This cylinder is the size of your forearm. It is lifting 70 tons. Every machine you are looking at right now runs on the same system. Different industries, different sizes. Pressures ranging from 50 bars to 500 bars. Some of these machines weigh 200 kilograms. Some weigh 200,000 tons. Inside every single one of them, the same three mechanical components, doing the same three jobs, following the same laws of physics. Most people who work around this equipment every day, operators, mechanics, engineers in training, can name those three components. They know the words. Knowing the words is not the same as understanding the system. There is one idea about how hydraulics work that almost everyone has completely backwards. It is the foundational concept. And if you have it wrong, nothing else about these machines ever fully makes sense. Not why pressures behave the way they do, not why systems fail when they fail, not why that cylinder the size of your forearm can lift 70 tons. We are fixing that today. 3 parts, 1 video. And by the end of it, you will be able to look at any hydraulic machine on Earth and understand exactly what is happening inside it. Here's why hydraulics seem complicated. If you try to learn the system from the outside, you see tubes, fittings, reservoir tanks, pressure gauges, relief valves, check valves, accumulators, coolers, filters, pilot lines. Some systems have 40 separate components between the tank and the working end, and most explanations of how hydraulics work throw all of them at you at once. Here's what those explanations get wrong. Most of those components are either safety devices, efficiency devices, or plumbing. They exist to protect the system, extend its life, or route fluid from one place to another. They are not the system. They do not do the work. There are only 3 components that convert energy in a hydraulic circuit. Every other piece of hardware exists to support these 3 or stop them from destroying themselves. Once you understand what's actually happening inside these 3 parts, not just what they're called, you will never be confused by a hydraulic machine again. You'll understand why an excavator can hold a full bucket suspended in midair, with the engine switched completely off. You'll understand why a hydraulic press generates 500 tons of force from a cylinder the size of a dinner plate. And you'll understand why the person who told you hydraulics just use fluid pressure was giving you half the answer at best. Let's start at the beginning. Part 1. The pump. I want to fix a misunderstanding right now before we go any further. It's the single most common misconception about hydraulics, and it is the reason the system never quite makes sense when people try to reason through it. The pump does not create pressure. The pump creates flow. If you run a hydraulic pump into a circuit with nothing blocking the outlet, no cylinder to push, no motor to turn, you get enormous flow and almost zero pressure. Fluid just pours out the end at high volume, no pressure. Now block that outlet. Put a cylinder in the circuit with a heavy load on it. Suddenly the flow has somewhere to push against, resistance. And resistance against confined flow is what creates pressure. Pressure is not something the pump makes. Pressure is what happens when the flow the pump makes meets resistance. This is not a semantic distinction. It changes how you diagnose every fault in a hydraulic system. Low pressure doesn't mean your pump is weak. It might mean your circuit has a leak and fluid is escaping before it can build resistance. High pressure doesn't mean the pump is working harder. It means something downstream is blocking flow more than it should. Remember this: the pump makes flow. The system makes pressure. Now, how does a pump actually move fluid? Most pumps on heavy machinery are positive displacement pumps. The name tells you exactly what matters about them. With every single rotation of the shaft, a fixed positive amount of fluid is displaced, trapped mechanically, and pushed forward. There is no slipping, no backflow, no bypassing. If the shaft turns one full revolution, a guaranteed measured volume of fluid moves forward. One revolution, one displacement. Compare that to a centrifugal pump, the kind in your home water system, which just spins a fan inside a housing and relies on centrifugal force to throw water outward. Centrifugal pumps are efficient and simple, but under high resistance, flow drops dramatically. At a certain point, they stop moving fluid entirely. That's completely unacceptable when you're trying to hold 70 tons in the air. Positive displacement pumps keep pushing regardless of resistance, right up to the limit of their mechanical strength. That's why they're used on every piece of serious hydraulic machinery. The most common type on large construction equipment is the axial piston pump. Inside the pump casing, a rotating cylinder barrel. Inside the barrel, usually 7 or 9 piston bores arranged in a circle. As the barrel spins, the pistons extend outward on one side, drawing fluid in from the reservoir, and retract on the other side, pushing fluid out under pressure into the circuit. The longer each piston strokes, the more fluid it displaces per revolution. What controls stroke length? A component called the swash plate, a tilted disc that the piston chews right against as the barrel spins. Change the angle of that disc, and you change how far each piston travels. More angle, longer stroke. More volume displaced per revolution. Less angle, shorter stroke, less displacement. Some pumps can go to 0 angle, 0 displacement, 0 flow, while the shaft keeps spinning. This is what allows an excavator operator to push a joystick further and get a faster, more powerful cylinder stroke, without the engine revving harder. The swash plate angle increases. More fluid per revolution. The engine speed stays constant, only the displacement changes. The pump's job? Create flow. Flow rate is controlled by displacement. Displacement is controlled by swash plate angle. Pressure is created by the rest of the circuit, not by the pump itself. That's part 1. Part 2. The control valve. If the pump is the heart of a hydraulic system, constantly pushing fluid forward, the control valve is the brain. It decides where that fluid goes, how fast it gets there, and what happens when the pressure in the circuit climbs too high. When you move the joystick on an excavator, any joystick, any machine, anywhere in the world, you are not directly connected to the cylinder. There is no cable, no mechanical link between your hand and the arm of the machine. What you're connected to is a control valve. Your hand moves. An electronic signal or a low-pressure pilot signal travels to the valve. The valve opens. The cylinder responds. The design that handles this on virtually all heavy equipment is called a spool valve. And once you understand how a spool valve works, you'll have the clearest possible answer to one of hydraulics' most asked questions. Here's the construction. There's a cylindrical bore machined to extremely fine tolerances, sometimes within a few microns. Inside that bore sits a cylindrical spool, also precision machined. The spool has wider sections called lands, which block or unblock a series of ports in the bore as the spool slides back and forth. When the spool is centered, the lands cover all the ports. Fluid cannot enter the cylinder. Fluid cannot leave the cylinder. The cylinder is completely sealed. This is why an excavator can hold a load in midair with the engine off. The spool is centered. The cylinder's ports are blocked. Hydraulic fluid is essentially incompressible. Unlike air, you cannot meaningfully compress a column of hydraulic oil under normal working loads. So that sealed column of fluid in the cylinder is effectively a rigid rod. The load pushes down. The fluid resists. The cylinder doesn't move. The engine can be switched off for hours, and the load will remain exactly where it was left. Now move the joystick. The spool shifts, let's say to the left. Port A opens to the pressure line. Port B opens to the return line, which leads back to the tank. Fluid flows in through Port A, pushes the piston, and the displaced fluid on the other side exits through Port B back to reservoir. The cylinder extends. The arm moves. Push the spool further. The port opening gets larger. More flow gets through. The cylinder moves faster. This is called metering. The valve precisely meters flow, like a throttle meters fuel. The speed of every cylinder movement on a modern excavator is controlled by how far the spool shifts, which is controlled by how far the operator moves the joystick. On modern machines, this happens electronically. A sensor reads your joystick position. An electronic controller sends a signal to a proportional solenoid, an electromagnet, which physically pushes the spool to a precise position matching your input. The whole process happens in milliseconds. This is why modern excavators feel responsive and proportional, rather than jerky and binary. But the control valve does one more critical job. Built into every hydraulic circuit, usually inside the valve block itself, is a pressure relief valve. This is the system's absolute ceiling. If resistance in the circuit pushes pressure above a set threshold, say 350 bar on a typical excavator, the relief valve opens a bypass path directly back to tank. Pressure can go no higher. The pump keeps running, the fluid keeps moving, but it's just circulating harmlessly back to the reservoir rather than building pressure that would rupture a hose or blow a cylinder seal. The relief valve is what makes it possible to build hydraulic systems that are genuinely powerful without being unpredictably destructive. It is the reason you can stall an excavator bucket against a rock without the machine exploding. The circuit hits the relief valve limit, fluid bypasses, and the system waits. Control valve. 3 jobs: direct flow, meter speed, set the pressure ceiling. That's part 2. Part 3. The actuator. The actuator is the output device. It's where all of that flow and pressure, generated by the pump, directed by the valve, finally gets converted back into mechanical work. Motion. Force. The thing the machine actually does. There are 2 types. Hydraulic cylinders produce linear motion, push and pull in a straight line. Hydraulic motors produce rotary motion, continuous spinning of a shaft. Between those 2 types, you can explain the working movement of every hydraulic machine ever built. Cylinders first. Because this is where the force multiplication of hydraulics goes from impressive to almost unbelievable. Pascal's law. The foundational physics principle behind every hydraulic cylinder. It states that pressure applied to a confined, incompressible fluid transmits equally in all directions throughout that fluid. The practical result? You can apply pressure through a small pump, transmit it through a thin hose across any distance, and recover that same pressure acting on any area you choose at the far end. The formula is 3 variables. Force equals pressure multiplied by area. F equals P times A. A typical excavator boom cylinder has a bore diameter of around 160 millimeters. The cross-sectional area of that bore is approximately 0.02 square meters. Operating pressure on a large excavator is typically around 350 bar, which in SI units is 35 megapascals or 35 million pascals. 35 million pascals multiplied by 0.02 square meters. The result is 700,000 newtons of force, roughly 70 tons, from a cylinder that's 160 millimeters across. This is why hydraulic presses can flatten cars, why log splitters rated at 30 tons run from engines you could carry with one hand. The force isn't magic, it's physics. Small area at the pump, enormous area at the actuator, same pressure throughout the fluid. Hydraulic motors follow the same principle, but instead of pushing a piston in one direction, fluid acts against pistons or vanes arranged around a rotating shaft. Flow in, shaft spins. Reverse the flow, shaft reverses. Stop the flow, shaft stops. No coasting, no overrun. Immediate, controlled response. Hydraulic motors drive the slewing ring on an excavator, the 360-degree rotation of the entire upper body. They drive the tracks on a bulldozer, the drum on a concrete mixer, the clamshell bucket on a dredge. Anywhere continuous rotation needs to be powerful, reversible, and precisely controllable, you'll find a hydraulic motor. That's part 3. Now let's put all 3 parts together and watch what actually happens when an excavator operator digs a trench. The engine runs the pump at a steady speed. The pump displaces fluid at a set rate, around 200 liters per minute, into the pressure line. With all the control valves centered, the cylinders are locked. Pressure in the line stays low because fluid is just circulating back to tank through the pump's bypass. The machine is at idle. Nothing is moving. The operator pushes the boom joystick forward. The directional control valve spool shifts. Port A opens to the pressure line. Fluid enters the rod end of the boom cylinder. The boom drops. Displaced fluid from the other end of the cylinder exits through the return line back to the reservoir. The pump registers the increased demand. The swash plate angle increases. More flow, same engine speed. Simultaneously, the operator rolls the wrist. The bucket curls. A second directional valve opens. Now 2 actuators are demanding flow from the same pump. The pump responds by increasing displacement further. Swash plate at a steeper angle. More fluid per revolution. Both cylinders move. Pressure stays within the designed working range. The relief valve never needs to open because the operator isn't stalling against anything. 3 cylinders, 2 motors for the tracks, 1 motor for the slewing ring, all fed by 1 pump, all controlled by their individual directional valves, all converting pressure into work through the same physics. 1 pump, multiple valves, multiple actuators. The entire machine, every single motion it makes, runs through this same architecture. A pump that creates flow. A valve that controls it. An actuator that converts it into work. That is the complete architecture of every hydraulic system ever built. Everything else is there to support, protect, or route between those 3. The excavator holding a load with the engine off, that's the valve, spool-centered, fluid locked. The concrete pump throwing mix 50 meters into the air, that's Pascal's law. Small bore, high pressure, enormous force. The car crusher, that's a double-acting cylinder at 400 bars, F equals P times A, playing out in about 4 seconds. You now see what most people around this equipment have never been shown. Once you see it, you can't unsee it.